In this video clip, I want to briefly discuss the purpose and the method of obtaining confidence interval. Now, every time we do an experiment, we collect data, we make measurements, and our data basically are nothing but a sample. So here we have our sample. These are our observations, these are our measurements, and the sample is characterized by its statistics. And the purpose mostly of doing an experiment is to make an inference about the bigger population and the population of which this sample has been drawn. So I indicate it like that. So that would be the overall population. And a population, of course, is characterized by its parameters. So, for example, we could look for the mean of a population, usually abbreviated with mu, or the variability, the variance of the population, that's abbreviated with this sigma square. And all we have, however, is just our sample statistics, so the mean of our sample statistic, which is usually abbreviated with x bar, and the variance, let's say, of our sample, which is abbreviated with s square. So all we have is our sample, and now we want to make some educated guesses about the population parameters. And the concept of the 95% confidence interval basically says, or not just 95% confidence interval, any confidence interval is that we say, right, we assume that our sample mean x bar actually somehow represents the population mean mu. So we would assume they are equivalent to each other. But of course, because we have only a sample, we cannot be sure that our sample mean is identical to the mean. So therefore, what we can say is basically that our population mean is somewhere within a certain range. Within a range around the sample mean. And we usually indicate that by x bar plus minus the margin of error. Margin of error. So if we just simply look at it in a visual representation, here we have our x bar, and this region here to the left and to the right of x bar, that indicates our range. Each bit here is indicated by the margin of error. And the whole part is actually called a confidence interval. Confidence interval. And what we are basically saying is that with this method of calculating a confidence interval, we get this range here, and we believe that our true population mean is located somewhere in this range. Of course, we don't know where it is, but we can sort of say there is a certain range in which this population mean most likely is located. And when I say most likely, we usually specify how likely we want this to be. So, for example, if we have a very narrow confidence interval like that, we can say, how likely is it that our true population mean is actually located in there? It's probably not terribly likely, but if we have a much wider confidence interval, we can say that it's quite likely that the true mean is located in that. So basically, the more certain we want to be that our true population mean is captured by this confidence interval, the wider this confidence interval will be located. Now, what can we do with this confidence interval? As I said, every single sample has its associated confidence interval. And we can say that if we go, let's say, for a 95% confidence interval, and I abbreviate it like that, in a 95% confidence interval, we can be pretty sure that if we took 100 samples and each sample with each confidence interval, we have 100 confidence intervals, basically. I don't draw 100 samples, but with this method, we would get 100 samples, and 95 of these samples have the true population mean within its range, within the confidence interval. Of course, if we just take one sample, we don't know whether this is one of the 95 samples that has the true mean in it, or whether it's one of the 5 samples that don't capture the true population mean. So we don't know. So there's a certain element of uncertainty, but with 95% confidence, we can be pretty sure that we capture actually the range in which we believe the population mean is located. And let's be absolutely clear, the population mean is a very clearly defined parameter. There's no uncertainty about the population mean in itself. The uncertainty comes from what sample we choose. And of course, we don't know whether this sample is actually captures it, but we have a 95% chance that it does. Now, what can we do with the 95% confidence interval? We can calculate our 95% confidence interval, and of course we can then compare it, for example, to a reference value. So for example, I put here a reference value, and we can treat this reference value as a population mean. And let's call this population mean 1. Now what we see is that we say from our confidence interval, we believe that the true population mean from which this sample derives, this population mean here, let's call this mu2, that is derived, is within this range here, within this confidence interval. That is what we say with the confidence interval. We believe that this population mean is located in here. And now if we compare that to our reference value, we can ask, is this reference value that is from a population, from another population, is this included in our confidence interval? And what we see here very clearly is the reference value not included, so that indicates that this reference value represents a different population mean. represents a different population mean and a different population altogether. So in this case, if the reference value is not included in the confidence interval, we can be pretty sure that we are talking about two different populations. One population represented by mu2 and the other population by the reference value. What happens if we have the following scenario? We have our confidence interval and we find that our reference value here is included in the confidence interval. So what this means is that we say, right, we believe that the population from which this sample was taken, mu2, the population mean, is included in this confidence interval. And now we have a second point estimate, that is our reference. Let's call this mu1 again. And in this case, we say that we believe that, or we know that this reference is included in this confidence interval. That means both mu1 and mu2 are equivalent. We cannot distinguish between them, and that means that we are probably we could be talking about two different populations, but we also could talk about one and the same population, because at the end of the day we don't know where mu2 is located. We know it is somewhere in this confidence interval here, but we don't know where it is. So it just as well could be this one here, our reference point. So that basically allows us to make a judgment when we have one sample and compared to a reference point. Now, what about if we have two samples? So here we have sample number 1 with its confidence interval, and here we have sample number 2 with its confidence interval. And the way I've drawn it is we can say, okay, we believe that the population of which sample number 1 is taken, that is here this one, represented by mu1, and sample number 2 is taken from a different population, mu2, which is characterized by mu2. And the way it is drawn here, we can say that our prediction for sample number 1 or population number 1, the mean here, and the mean for the population 2 are very different. So that means that immediately indicates that we are talking about two different populations. Two different populations. So if there is no overlap in the confidence intervals, we can be pretty sure that there are two different populations. Now, what if we have this scenario? And so what this tells us that we have two samples, and we make a prediction that our population for sample 1 is located in this range here, and for the second population it is located in this range here. So basically this boils down again to what we discussed in the previous screen, where we looked at this case where we had a reference point, only that in this case the reference point sort of has also some uncertainty. So in this case we cannot distinguish whether we have two populations or one population. So that's also quite straightforward. Now, what if we have this case here? So we have one confidence interval for our sample 1, and we know that the population mean is most likely located in this region, and we know that we have for our second population, the population mean is located in this region. And what we see is that there is an overlap between the two. So this, of course, doesn't allow us immediately to say, oh, actually, is there a difference? Are we talking about two different populations, or are we talking about potentially one population? So we can't actually immediately say anything about it. But what we can do is we can say, in this case, we can actually say we calculate the difference between these two populations, and or between the samples. So we can calculate the differences, and what we find is that, again, we can, for this, we can treat this as a new sample. So this can be a new sample, and I call it just as delta mean. And if we do that a lot of time for different samples, we again could calculate for a number of different samples. We can calculate a confidence interval, but this time we would have a new mean that would be this one here. So what we are doing here is basically we say, what is the mean of the differences here for the difference between the two samples? And again, we can determine a confidence interval. Now, of course, we are quite interested in does this difference actually contain the value of 0? So is 0 included in this difference? Why is that important? Why is that of interest? Well, if 0 is included, we say our difference could be anything, including 0. And if there is a 0 difference, then this means that our two sample means here represent potentially the same population. So basically, let's recap. If we have overlapping confidence intervals, we need to do some statistical testing in order to find out whether actually these two samples come from two different populations. If, as I outlined here, the confidence interval are totally overlapping, then it could very well be that the two samples come from the same population. We still can't totally rule out that they come from different populations, but we can say it's likely that they come from the same population. And if the two confidence intervals are way apart from each other and don't overlap, we can say with a high degree of confidence that these two samples come from different populations. I hope this makes sense, and thank you for watching.